Okay, here we've got a really nice energy-based question. As ever, I really hope you've tried this. If you've not, go off, find it. The name is in the title of this video, hopefully. Okay, and again, press pause, try the question, and please do let me know if there's anything you don't understand. Okay, so we've got a simple torch. It's got a battery connected to a lamp. First one, very common question, state the name of the energy store in the battery. Batteries are a store of chemical energy. I've given a couple of other examples here, bread, coal. Okay, chemical energy stores are ones which release energy due to chemical reactions. So combustion, for example, or respiration in terms of food. Okay, in terms of the battery, we've got essentially a chemical reaction within the cell. We've got acids, etc., reacting with metals to provide this flow of current. So it's chemical energy. Common misconception is that it's a store of electrical energy. Electrical energy in GCSE terms is an energy transfer. We talk about electrical work. That's actually what I'm describing in the next bit. Describe how energy is transferred from the store to the lamp. Well, what we've got is the flow of electric current. Electric current flows from the battery to the lamp. Now again, that description is not very good. I probably should be saying it flows in the circuit, but we get the idea here. We've got the flow of electrons around our circuit carrying that energy from the cell or the battery to the lamp. And then we've got some calculations to do. We've got a ball of mass 0.56 kilograms dropped from a height of 9.4. You notice here these numbers are a bit awkward. We've got 0.56, 9.4. We're going to use our equation here, EP equal mgh. Now this is a nice one, it's just multiplying. However, it relies on you knowing g. Notice that g is not given. We're given the mass, we've got the height, but we do not know g. Well, 0.56 times 9.8 times 9.4, because we know all those values. And that comes out as 51.59, which is 51.6, which to three significant figures. Now, I think a lot of students, when they're doing these questions, get worried about significant figures. CIE seems to like occasionally putting things to two significant figures. You will not be penalised if you write this to three significant figures. Generally, 3 or 2 significant figures are enough. So even if the mark scheme says 52, then you will not be penalised if you write 51.6. They're not going to take that mark away. They know you've done the right work because you've written down your working. Okay, the worry there would be if you wrote it down without doing the working, and you might miss out on getting the appropriate marks. Okay, we're then asked to calculate the speed. Now, this is quite an interesting one because there's a difficult way of doing this, and there's a kind of there's a direct way and a roundabout way. We're actually doing the roundabout way here. Right? What we're going to say here, we're going to calculate the speed at which the ball hits the ground, and we're going to assume that air resistance is negligible. Negligible means you don't need to worry about it. So we don't need to care about air resistance here. We're just going to think about the energy. The energy at the top equals the energy at the bottom. So in falling, we are losing 51.6 joules. So actually, at the bottom, we're going to gain 51.6 joules of kinetic energy. We know our kinetic energy is 51.6 at the bottom. We know half mv squared. We know m. We need to know v. So we're going to calculate v squared, which is 184.3, and we're going to get a v, which is square root of this, which is 13.57. Again, I've given too many significant figures there, so I've changed it now to 13.6, and I think I remember on the mark scheme this was 14 meters per second. Again, two significant figures versus my 3 here. Do not worry about that. Don't go any more than 3 because that will be probably deemed TMI, too much information. Okay. We're then told that the ball rebounds to a height 8.2. Now that's reassuring because that's less than 9.4. Okay, so you can already predict what we're going to ask here. Firstly, they ask us why we don't reach a height of 9.4. Now, I'll be honest with you, I don't know if my answer really agrees with the mark scheme. What I talked about was energy losses, okay? And my original thing was thinking about energy losses. Now, the key thing for me with energy losses is one thing that comes to mind immediately for me is the fact that when you drop a ball on the ground or drop anything, it makes a noise, okay? So you are losing energy. That energy has to come from somewhere, okay? So you are going to lose energy. Now, energy will be dissipated in various forms, okay? One of them is to sound energy from the collision. One of them is to thermal. The ball, believe it or not, will actually heat up as a result of the collision with the ground. But the bit that they put in the mark scheme was also about work done in deforming the ball. Now, this is where it's really tricky for teachers. Because if I was going to give advice without seeing the mark scheme here, I would say focus on the idea that energy is going to be lost in some way. Okay, energy is dissipated. In other words, that initial GPE, the final GPE is going to be less than the initial GPE. Okay, and then define how it is. So I've kind of loaded out all the work done in deforming the ball. It's going to change its shape. It's going to make a sound. Okay, and it's also going to heat up in the collision, and that would be enough here. Just because it's not in the mark scheme doesn't mean that it can't gain marks, as long as you are being sensible with your suggestions. Okay, so just bear that in mind if you're looking at past papers, etc. There's always credit for sensible suggestions. Okay, let's look at the last bit. Okay, percentage efficiency. Now I like this one because this is something I've actually done in lessons. The percentage of efficiency is given by the ratio of the energy out, the useful energy out, to the energy in, timesing by 100, of course. Now, if you notice here, we've got gravitational potential energy in, and then gravitational potential energy out. So mgh, I'm calling it h2, divided by mgh1. Okay, so therefore we're going to take the ratio of the height at the end to the height at the beginning. We don't need to worry about m and g because they cancel, and so therefore we're going to take 8.2 divided by 9.4, which is going to give us 87.2%. Again, if you notice here, if you've made a mistake, let's imagine you got the numbers the wrong way round. Let's imagine you said, actually, I've got 9.4 over 8.2. You're going to get a percentage which is greater than 100%. If you get a percentage which is greater than 100%, you have broken physics. Congratulations. Okay. However, you're going to go back and revisit that because that is not possible. All of our answers have to make sense within the context of the conservation of energy.